You've probably noticed it. You look at a massive, ultra-high-budget CGI movie, and despite all the raw computing power, the advanced ray tracing, the absolutely incredible digital art, something just feels a little off. Why is it that certain digital materials in modern CGI still fail to look completely, indistinguishably real? Well, it's a fascinating question, and honestly, the answer lies way deeper than you might think.
Welcome to today's Explainer. Today, we're unpacking a truly mind-bending paper published in June 2026, titled Rendering Coherent Scattering via Quantum Collision Models. Authored by an incredible team of researchers, Joan S. Ferreira, Spencer S. Topol, Pierre Fromholtz, and James R. Wooten, this research proposes a radical, and I mean radical shift in how we render digital light. It is absolutely incredible to explore, so let's get into it.
Here's a quick roadmap for today. We're going to look at the limits of current CGI, what happens when light meets matter, quantum collisions explained, rendering the chaos, and finally, a quantum leap for graphics.
All right, Section 1, the limits of current CGI, and the problem with static assumptions.
According to the researchers, the fundamental limitation of how classical rendering and ray tracing operate right now basically comes down to a single assumption. See, traditional light rendering techniques treat the optical properties of materials as completely static. So what does that actually mean? It means the computer assumes the material itself doesn't fundamentally change just because light is hitting it. But as the paper points out, this assumption breaks down entirely in the real world. In reality, material properties dynamically evolve in response to incident illumination. Basically, real matter reacts to light, whereas current CGI assumes it just sits there passively. Think about a thin, waxy leaf on a tree. The moment intense, blistering sunlight hits that leaf, its physical properties might subtly change on a microscopic level, totally altering how the light scatters. Traditional rendering? It just ignores that dynamic reaction entirely. Moving on to Section 2, when light meets matter, the paradigm shift. To really visualize this paradigm shift, think of the traditional approach kind of like playing a game of pool. Because of those static assumptions we just talked about, classical rendering treats light bouncing off materials like perfectly predictable billiard balls. A light ray hits a surface, bounces off, and the math is relatively straightforward. But the researchers' novel shading framework captures dynamically evolving properties. It acknowledges that when coherent light interacts with matter, they actually influence each other, interacting a lot more like complex waves. The light and the material are basically engaged in this dynamic shifting dance rather than just a simple static bounce.
Section 3, Quantum Collisions Explained. Let's demystify the core solution.
So how do we fix this? The researchers propose a quantum collision model. They're actually combining classical ray tracing with this quantum model to explore coherent light-matter interactions. Instead of treating light as just a simple digital ray, this novel shading framework treats both the incident light and the material excitations as tiny, interacting, quantized modes. They are literally shifting away from classical physics entirely just to capture the true, microscopic reality of what happens when light hits a surface. It completely changes the foundation of how we simulate reality. Now, before we look at their specific pipeline, we need to quickly anchor a highly technical term they use throughout the paper: BSDF, or Bidirectional Scattering Distribution Function. In the context of this research, you can just think of a BSDF simply as the digital rulebook that dictates exactly how a material handles and scatters light. Literally every material in a video game or a 3D movie uses a BSDF, so the computer knows how it should look. The ultimate goal of this new quantum model is to generate vastly superior standard rulebooks. To achieve that, the paper outlines a specific three-step pipeline. First, they break the light and the material excitations down into those quantized modes we were just talking about. Second, they smash them together, modeling the scattering of that light as unitary collisions. And third, they hand that massive mathematical headache completely over to quantum computers to pre-compute. By structuring it this way, they managed to take heavily theoretical quantum physics and turn it into a highly practical, working pipeline for actual rendering. This gets genuinely fascinating when we look at subsurface scattering. Subsurface scattering is what happens when light enters a material, bounces around inside it for a bit, and then exits. It's like holding a super bright flashlight up to your hand and seeing the light warmly glow through your skin. Under this new framework, this incredibly complex optical event is modeled as a sequence of symmetry-constrained unitary collisions. By framing it as a sequence of quantum collisions, the math can finally account for how the material's properties actually evolve while that light is busy bouncing around inside of it.
Section 4, Rendering the Chaos, an Artistic Frontier.
Now, while this might sound like a purely chaotic math problem, it actually unlocks a massive artistic frontier. Because this formulation successfully accounts for dynamic evolution, it allows developers to incorporate entirely new optical phenomena that were previously impossible or at least incredibly difficult to fake. We are talking about non-integrable dynamics, chaotic optical responses, and wild multi-layer interference effects. Imagine the dizzying, constantly shifting colors of an oil slick, or the incredibly complex, layered iridescence of a butterfly wing, but rendered not by some cheap approximation, but by actual quantum-level physics simulation. This matters immensely for the 3D art community because it fundamentally raises the ceiling on what is visually possible. These chaotic responses and multi-layer interferences are the absolute key to creating what the researchers call physics-inspired materials. Think about how groundbreaking this is. Artists will no longer have to spend hours hacking together fake layers and complex shaders in a game engine just to mimic reality. Because the rendering engine isn't relying on those old static assumptions anymore, the physics will just naturally do it. Developers can generate materials that react to light in distinct, hyper-realistic ways. They possess true optical signatures, meaning they behave exactly as their real-world counterparts would under literally any lighting condition.
Finally, Section 5. A quantum leap for graphics. The future of rendering. Now you might be wondering, and it's a fair question, do I need a liquid nitrogen-cooled quantum computer sitting on my desk just to play the next generation of video games? Thankfully, no way! The paper highlights the extremely exciting technological reality that these massive collision operators can actually be pre-computed. Researchers plan to use near-term quantum computers to do all the heavy lifting beforehand. They basically calculate the incredibly dense quantum collisions in a lab and then use that data to generate standard BSDFs, those digital rulebooks we mentioned earlier. That standard pre-computed rulebook can then just be slotted right back into the traditional rendering engines we already use today. It's brilliant!
So, to bring it all together for you, this framework successfully bridges classical ray tracing with quantum models. It finally retires those old, rigid, static assumptions in favor of truly dynamic, evolving materials. And best of all, it's completely practical, utilizing near-term quantum hardware to do the heavy lifting safely behind the scenes.
Which leaves us with this final, mind-bending thought to close out today's explainer. If we are standing right on the precipice of using quantum computers to perfectly simulate how light fundamentally interacts with matter, what previously impossible digital realities will we build once quantum computers render our light? The frontier of 3D art is about to look more real than reality itself. Thanks so much for joining this explainer, and keep seeking out the fascinating structures behind the digital world around us.